We are continuing with Chapter 9, the Pythagorean Theorem. This section 9.3, we're going to start talking about special right triangles. So our learning target here is I can apply the Pythagorean Theorem to solve problems. The 30, 60, 90 triangle is one of two special right triangles we will be investigating. The special nature of these triangles is their ability to yield exact answers instead of decimal approximations when dealing with trigonometric functions, which we'll talk more about this semester as well. So before we start the lesson on the first special right triangle, the 30, 60, 90, I want to caution you that this is a special right triangle, and the concepts that we're going to learn in this video can only be applied to special right triangles. Students tend to want to apply this to any triangle once we go over this, but it can only be used for triangles that have acute angles of 30 and 60, right triangles that have acute angles of 30 and 60. So let's go ahead and get started. We're going to start with an equilateral triangle, and we're going to draw an altitude or a height down the middle. All right, and then since this is an equilateral triangle, this altitude is also going to be a median, so it's going to divide this side into two congruent parts. And in the directions here it says given an equilateral triangle with side length 2a. So this side length is going to be 2a, and this side length is going to be 2a, and this bottom side of the triangle is also going to be 2a, but I'm going to split it up into a part that's a over here and a over here, and then if I added those together I would get 2a. So what we want to try and do here is find the height of each of these right triangles that make up the large equilateral triangle. Before we do that, what I want you to notice here is that this is the short leg of our triangle here. I know this angle is 60 because it's one of the original angles of the equilateral triangle, and this angle is 90, and this altitude is also an angle bisector since the triangle is equilateral, so this is going to be 30 degrees. So here's how we get our 30, 60, 90 triangle. We take our equilateral triangle, we draw an altitude, and divide that 30, 60, 90 basically in half, and we get a 30, 60, 90 on the left, and we would also have a 30, 60, 90 on the right. So this short leg here, I know it's the short leg because it's opposite the smallest angle. Here's my 30-degree angle. So if I go opposite that, that's going to be my shortest side. And then here's my 60-degree angle, so that's going to be my next biggest side, and of course the hypotenuse is opposite the right angle, so here's my right angle. If I go clear across the triangle, there would be my longest side. So I can already see that this short leg is half the length of the hypotenuse. And now we're going to work on what this longer leg would be. So it's a right triangle. I'm going to use the Pythagorean theorem. So I have a squared plus h squared is equal to 2a squared. Just applying the Pythagorean theorem, we just don't have very many numbers in this equation here. So let's go ahead and simplify a little bit. I have a squared plus h squared. When I square 2a, I get 4a squared. And then I'm going to subtract a squared from both sides. So those cancel out, and I'm left with h squared is equal to 4a squared minus 1a squared is 3a squared. And to solve for h, I'm going to take the square root of both sides because square root and square are inverse operations. They undo each other, just like addition and subtraction and multiplication and division. So I'm going to split this up. One of our properties of radicals is that I can give everything under the radical, as long as it's multiplication or division, I can give it its own square root. So I'm going to split that up into the square root of 3 and the square root of a squared. So this square root and that square cancel. So I'm left with h, which is what I wanted. and this square root and that square are going to cancel, so I'm left with an a root 3. Alright, so this side here turns out to be a root 3, and normally we would put the coefficient in front of the variable, but here we're going to put it after so we don't make the mistake of thinking that the a is underneath the square root. So here's what we've got. We've got a hypotenuse of 2a, a short leg of a, and a long leg of a root 3. So I know it doesn't seem like much right now, but this is the ratio of the sides of any 30, 60, 90 triangle. So here we've got our box here. We've got 30, 60, 90 triangle. So in any 30, 60, 90 right triangle, the ratio of the short leg to the long leg to the hypotenuse is always, so we've got a to a root 3 to 2a. So this value of a could be anything, and then the ratio would still be the same. Or how most of the time we're going to look at it, we're just going to reduce this down to 1 to root 3 to 2. Alright, and this is how we're going to use that ratio to help us solve problems. Now, I know this video is a little bit longer than most, but you may want to rewatch this one more time just to make sure you understand the concepts and get all your questions answered. And we'll see you in the next video.